Yeah, as Joachim already said, I've done quite a lot of work recently on fractions and more specifically on fraction magnitude. I will in a minute say what I mean by that. And in this talk I'm going to focus also on a phenomenon that has been discussed a lot in the literature recently on fractions, which is the phenomenon of the natural number bias. And one thing that I would like to discuss with you at the end of the talk is whether this is actually a good notion to describe the phenomenon that we mean. Because I'm not an expert in bias research as such, I'm just focusing on this kind of bias, which has been called bias, but we could discuss whether this is actually a good term to describe what we find here. Yeah, and as a general framing here, so much of my work is actually located at the intersection between math education and cognitive psychology, or numerical cognition more specifically. So what I'm really interested in, what I'm trying to do in my work is to combine different perspectives, because what I notice is that very often there's a rich literature in the cognitive literature on fractions that is not so much cited in the math education literature, and vice versa as well. So I would like to just very briefly say a few words. Why am I doing research on fractions and why are fractions so interesting to study? Well, of course, we need sometimes fractions in everyday life, but maybe not as much as we think, as we learned from Stefan this morning. But fractions are, of course, a key mathematical concept within the domain of numbers. We need fractions to construct number domains. But there is also empirical evidence that fraction competence predicts later success in mathematics and higher education more generally. So even if studies control for a number of other variables, fractions seem to be a particularly good predictor of later success. So there must be something about fractions that if people understand fractions, it's a good thing for later mathematics. Now, recently there has been a lot of research again in the math education literature and in the cognitive psychology literature after fractions have already been studied in math education for decades. And the reason is probably that we still have not really understood very well what is going on in our minds when we think and reason about fractions. And one thing why fractions are still of interest to study, one reason is that many students struggle a lot with fractions, and they do so even though we have studied fractions for decades in math education. And we find that also not only younger students, but even older students and even adults struggle a lot with fraction problems. And I would like to focus on one specific aspect that makes fractions difficult, or that many people struggle with, and that's fraction magnitude. And I will show what I mean by one very nice example, I think. If you think about this problem, 12/13 plus 7/8, please give the best answer out of 1, 2, 19, or 21. And I'm pretty sure you did that very quickly right now. So how you can solve the problem is you can use an algorithm which says multiply both fractions to get a common denominator, which would be 104. Then you can divide the fraction, then you get 1 and 83 over 104, and this is approximately 2. But of course, it's probably not what anybody here in this room just did. A much more efficient strategy is to say that both fractions are approximately 1, so the correct answer must be 2. What you need to do that is what I call an understanding or a sense of fraction magnitude. So you had a very quick idea that both fractions are approximately 1. Not exactly, but approximately. And it's an interesting phenomenon, because probably you have not reasoned very often about the fraction 12/13 in your life so far, but still you were able to do that very quickly. And this is what people have called a number sense for fractions, or fraction sense, or fraction magnitude, depending on the literature. Now, this is something that we also want students to be able to do. But if you look into textbooks, this is not something that is supported there very often. What you do find is the algorithm, how to add two fractions, right? And this particular item here has been used in a in a study with a representative sample in the United States in the 1980s, and the numbers were so they found that just 24% of 13-year-olds, that is students after having received intensive instruction on fractions, could solve this problem correctly. Which shows that this is a key problem, that students can often manipulate the numbers, but if they are asked to give an estimation or to have a quick idea of how big the fractions are, they fail to do so very often. What they do instead is something else, and this is probably what you can just speculate what the students did who choose these other answers, 19 and 21. There are pretty good ideas about that. If you add the numerators, 12 plus 7 gives you 19. If you add the denominators, 13 plus 8, it gives you 21. And there is a lot of other research that shows that componential addition is the most frequent mistake that students make with fraction addition problems.
Which age?
So these were 13-year-olds, and this was in the US, and you can say it was in the 1980s, but another study in 2015 found very similar results, and there are many other studies with German samples and with others actually across the globe, and they find very similar results. So this is a very well-known key problem. Now, the question is, where do such mistakes come from, and what could be the reasons why it's so difficult to understand the fraction mathematics? And one of the theoretical frameworks that has been proposed is a conceptual change framework, which means that one of the reasons why people struggle with understanding fractions as numbers and as magnitudes is that they have formed a very stable understanding of what whole numbers or natural numbers are, for that matter. I'm just focusing on natural numbers. It's not, you could replace it with integers more generally, but I'm just focusing on the natural numbers. And then, so for years, students are used to reasoning about natural numbers. Now, when you extend the number domain to rational numbers or positive fractions, for that matter, it's very difficult for them to get that change in their concept. So that's what conceptual change means, and I will talk about that a little more. That there is a need, so students need to change their concepts that they have formed about natural numbers, and these concepts seem to be very, very strong and very, very stable. And another framework or theory that has been proposed here is if this change has not happened, this leads to systematic bias, which has been called natural number bias. So systematic mistakes that students make because they rely on the reasoning about natural numbers. And so there have been different dimensions where students would go wrong if they do not make that change. And they can be described pretty easily by mathematical differences between the set of natural numbers and rational numbers. So, for example, there is a dimension of representation. Within the natural number set, every number has just one unique representation. Number 2 has just one symbol, 2. But that's not true for rational numbers anymore. Rational numbers have infinitely many representations, and a typical error, as you can see on the right side, would be for students to think that a half and 2/4 and 0.5 is not the same number because they have different representations. And this is actually very well documented, so lots of studies have found that this is actually something that students make very often. Another aspect is the operations. So within the natural numbers, multiplying a number makes a number bigger, and that's an idea that is not true anymore for rational numbers in general. So students would often argue that if you multiply 4 by a number x, it cannot be smaller than 4. So on the right-hand side, it's always an error that is printed there. The issue of density is also well studied. Within natural numbers, each number has a unique predecessor or successor. So if you have number 5, there is number 4 comes right before it, number 6 comes right after it. That doesn't work for rational numbers anymore. There are no predecessors or successors, but many students would argue that 2/5, after 2/5 comes 3/5, and there are no numbers in between, which is not true within the rational number set. And finally, another aspect is size or size comparisons. So within the natural numbers, you can easily compare numbers digit by digit from you go from left to right, and the first digit that is larger in the one number is a larger number. But that doesn't work anymore for fractions. You have to think about the relation between two natural numbers, which is actually a very complicated idea. And it does so. The rule that you go for the larger number that we see doesn't work anymore. But that's what many students would do. They would say that a fourth quarter is larger than a third because 4 is larger than 3. And so in the rest of my talk, or in our talk, we are going to focus on this last issue here, on the size issue. So fraction comparison problems have been studied for some years, actually, because there are very clear patterns that people find in this mistake here. But the question that I'm going to focus on is what's exactly the reason for such patterns? So the pattern, so on the last aspect here, the pattern that has been described very often and which has been named the natural number bias is in general it has been defined sort of as a use of natural number properties to solve rational number problems. And as you saw on the last slide, in general, natural number principles do not apply to rational numbers as a whole, but sometimes you actually would be right if you do so. As empirical evidence that has been taken as evidence for a natural number bias has been the better performance on congruent versus incongruent problems. So you can construct rational number problems that are either congruent or incongruent with naive natural number reasoning. And this is, in the case of fraction comparison, you can construct items such that simple comparison would lead you to the correct answer. But in the first case, you can say, well, 4 is larger than 2, so the left fraction must be larger, and that's actually true. But on the right example, if you say 4 is larger than 3, so a fourth must be larger than a third, it's actually wrong. So you can systematically categorize fraction comparison items as being congruent or incongruent, which are naive reasoning or comparison of the numerators or the denominators. So that's important to understand here, the difference between congruent and incongruent items. And much of the literature has actually looked at accuracy and or response time differences between these two different types of items and found a very clear pattern, which is people are systematically better in congruent comparisons rather than incongruent comparisons, probably because they rely on the natural number reasoning. And this has been found in younger students, older students, adolescents, and even in adults. But the question, what has been not very well understood here, is whether this is a very general pattern that would even occur in people that have a good mathematical understanding and that do not really have no severe misconceptions about fractions. And the second thing that has not been really understood or studied is, does such a pattern occur in more complex comparisons? Because as you can see here, these are very special cases. In the left case, you have common denominators, and in the right case, you have common numerators. And many studies have actually only used such items to compare the congruent and incongruent cases. And we wanted to know, does that occur also if you have more general fraction comparisons when we have no common numerators or common denominators? You can classify such items, many of them, also as congruent and incongruent. So, in the rest of my talk, I would like to ask the question, do we find such a natural number bias in mathematicians? So people who have very high understanding of mathematics and probably also fractions and rational numbers. And then how is that related to fraction magnitude processing? And then I will just briefly show a study with school students where we also looked at this relationship. And then finally, Johannes will show you a little bit how we go about that in an intervention study where we try to enhance students' fraction magnitude understanding. So the question here was, do we find a natural number bias in mathematicians? Because that would be, suggest that this could be something that is really hard to overcome, so that everybody maybe has such an intuition that if you see these numbers, you very quickly think, okay, this must be the large fraction. Maybe you can then inhibit your response and then come to the correct answer. So that's why people are interested not only in accuracy but also in response times, because even if people are accurate, could be that there is a response time difference. So we studied a sample of academic mathematicians, and we had a sample, so on a computerized experiment, they saw one fraction comparison item after the other. They were asked to respond as fast and accurate as they could. The items were either congruent or incongruent, and we had pairs with or without common components, so some that had common numerators, common denominators, or either no common components at all. So what we found is, so first of all, those people were extremely accurate on these problems, so accuracy rate of 97%, and they were also really fast, like about 3 seconds per item. And when we look at the difference between congruent and incongruent items, we do find a significant difference for the common component set. So these are just 2 examples, so fractions that had either common denominators, common numerators. But when we look at the set without common components, we did not find that pattern. On the contrary, we actually find a trend to the reverse pattern. So people tended to be faster on the incongruent set rather than on the congruent set. So for example, these problems here. So what this suggests here is that this bias pattern, better performance on congruent rather than incongruent, is maybe not a general pattern that we find in all people and in all items. And you could say here, well, is this actually a bias, or is it just a very efficient heuristic? Because on the left side, when you compare these fractions, it's actually a very clever idea not to compare the magnitudes of the fractions as a whole, but just to compare the numerators or the denominators respectively. So the question is, maybe this is not, bias is maybe not the right term here, maybe it's just an efficient heuristic that people use when they can use it very efficiently in such situations. And if you cannot use it on the right-hand side, people are much slower, but then you would not find the bias pattern. So what we assume here is that on the left-hand side, when fractions had common components, people were actually not at all reasoning about the fraction magnitudes. And that's interesting because in the literature, the assumption has been made that there is sort of an interference of the whole number of components of the fractions with fraction magnitude processing. And this doesn't seem to be the case, because when we looked at fraction magnitude processing, and yeah, I will show you that, we actually find that these people did not at all think about the fraction magnitudes when the fractions had common components. So I just show you a little bit how do we measure fraction magnitude processing. And that's a very common method in the literature which has been used to assess natural numbers, which is called the distance effect. If people compare 2 numbers, they have been found to be faster when these 2 numbers are further apart than when these 2 numbers are close together. So people are, for example, faster to compare 2 and 8 versus 2 and 3. And the reason, the assumption is that people represent number magnitudes on a sort of mental number line, and if these numbers are further apart, it's easy to see that one is big and one is small, but if they're close together, it's harder to make that decision. So, So the effect, so this is a representation of the distance effect. If you plot response times depending on the differences between numbers, you would find such a decrease, meaning that as the differences increase, items get easier. For fractions, this is not so clear, because this would be a measure of whether people actually rely on the magnitudes of the fractions to compare the fractions. And it's not clear that people actually rely on the magnitudes, because you can use a lot of different strategies to compare 2 fractions, so it's not clear whether you would rely on the magnitudes. And there has actually been conflicting evidence, which could probably be explained by the selection of the specific items. So when we looked at the distance effect in our sample of mathematicians, so that's the same data here, we see a very clear difference between the no common components and the common components items, which shows that in the no common component condition, we find a very clear distance effect with an R square of approximately 50%, which is a pretty high variance explanation here. But we do not find a significant effect of distance of fractions for the other item set, which now suggests that it makes a lot of sense that in these cases, people did not even think about the fraction magnitudes, but they simply compared the numerators or the denominators. So for us, that's not really surprising, but for the literature, it was not at all clear what's going on here, and we could confirm such patterns with eye tracking measures, where this is just two examples, where we looked at the gaze paths of people when they solve these problems. These are just three examples. If the fractions had common numerators, people focus much more on comparing the denominators, vice versa for common denominators, and they have a very different pattern if the fractions do not have common components at all. So this all suggests that these mathematicians were able to adapt the strategy, either looking at the fraction magnitude or just on the components, very flexibly, depending on the problem type. Now, we wanted to look at this in school students because it's not so clear what happens there, and also to look at this in combination, natural number bias and fraction magnitude, because what seems to be really obvious, I think, now is that this should be combined. So far, the natural number bias literature and the fraction magnitude literature has been pretty much separated. So we did a very similar study with a similar item set, but it was actually different. But it was also fraction comparisons with a larger sample of 6th grade students. So these are students who have just been introduced to fractions in Germany. And what we found here, so we were looking not just at the general pattern across the whole sample, but we were looking for clusters within the sample, because we had the assumption that there may be groups of students that have very different and maybe very, very different patterns. And that's also what we found. So here you can see the solution rates, the accuracies for congruent and incongruent items. And this is one group of students who show a very clear typical bias pattern. They solved almost all congruent items correctly and almost all incongruent items incorrectly. And then we found another group of students who did exactly the reverse. So they had very high accuracy for incongruent items compared to congruent items. And then we found a third group of students who had also accuracy not really high, because we have the 50% chance rate here, but it's actually significantly above chance rate, but still, and this group did not show the bias. And if you look at the response times here, it's also a clear pattern here. It's the two bias groups, so the typical bias and the reverse pattern, they're very fast in their decisions, probably because they were not at all aware how to compare, or they didn't know how to compare fractions. They just used a very simple strategy, which is sometimes correct, but sometimes not. But the third group of students were probably more able to reason about the fraction magnitudes and were therefore slower. And this is also confirmed by the distance effect. So this was a more complex model, but the effect of distance was significant only in the no bias group, but not in the two other groups. So suggesting again that there was this one group of students who was able to reason about the fraction magnitudes, whereas the other students used a very simple heuristic, but not in a very intelligent way. They used it, but they failed in many of the problems. All right, so I would end this part with a first discussion. What I showed so far is that 6th graders, what you find here is 6th graders often use naive reasoning based on natural numbers to compare fractions. So they use either a larger component is larger fraction heuristic, or a smaller component is larger fraction heuristic. And this has been called the natural number bias. And what Johannes is now going to talk about is that enhancing students' ability to quickly activate fraction magnitude may probably also reduce their bias, because so the idea is to focus, to help students focus on fraction magnitudes as a whole, rather than to focus on the components separately. But the evidence that I showed for the mathematicians suggests that the natural number bias in fraction comparison may sometimes reflect the use of efficient heuristics, namely when the fractions have common components, for example, in people who have the knowledge to know when this heuristic is very efficient and when it is not. So We have had quite some discussions whether the term bias is correct or is a good term here, because for the students, we could say it's not a bias, it's maybe just a misconception or a lack of understanding of fractions. For the mathematicians, it's not a bias at all, maybe it's just a very efficient heuristic. So that's something I would like to discuss in the end. But now I would like, okay, we have a few minutes left, I think. For the last part, which would be the question that we are now trying to answer is, what happens if we support students explicitly in quickly activating fraction magnitude? And it's important to understand, so this isn't going to be an intervention study here, but it's important to understand that this is not supposed to be a very broad instruction into fractions, but it's supposed to be a very narrow, very focused training of fraction magnitude processing. And I will hand over to Johannes at this point.
Okay, thank you also from my side for being invited here and being able to talk to you. My name is Johannes Rosenkranz, and I'm a secondary school math teacher and a PhD student for Andreas. And I've been since 2018. I've been working on this project. We call it Fraction Magnitude, FracMag, which is about enhancing students' fraction magnitude. And I'm going to tell you a little bit about a digital tool we developed to help students gain fraction magnitude, and then the design of our study, and also a little bit about the test instruments that we used. So, supporting fraction magnitude. In the literature, there is evidence that visualizations can help process magnitude information of fractions. So, for example, in this example here, 3/5 and 4/7, it's not so easy to quickly decide which one of these two fractions is the larger one. But if we have, for example, two tape diagrams where we visualize each of the fractions, this becomes a lot more easy. And the crucial part here is that the step that we go away from counting the parts here to comparing the areas of the tape diagrams. And if we have this representation of these two fractions, this is something that even children at a very young age can already decide which one is the larger one. The idea is a digital tool that was based on the fractions magnitude, the fractions tutor, which is work that Andreas did with Martina Rau in Madison, and with the goal to enhance 6th graders' fraction magnitude. And as I just explained, we were drawing heavily on continuous representations to avoid this focus on whole numbers and counting of the parts, which we think is a very important step to understand magnitude. So, for example, I brought two items of this digital tool that we developed. This is one where students had to mark the fraction on the tape diagram, and they could do this. I'll just play this video here. So they could do this by continuously filling in or choosing the correct position, and then clicking this button. And if they're within a certain range, they would get the response that was correct, or that it was close, or that they were too far away. Another task was to compare two fractions. I don't know if you can read that very well, but it was asked to compare which one is the larger fraction, 1/7 or 2/6. And they had two number lines, and they could mark on each of the number lines, they could mark the fractions. So here the first position is 1/7, and they got feedback on that, whether that was the good position. Then on the second number line, and then choose the larger fraction. So very much always the thing, we have the fraction symbol, and then we have a magnitude representation of the fractions. Okay. So now we use this tool in an intervention study. We had about 300 sixth grade students, and we divided them randomly into 3 groups: an experimental group, a control group 1, and a control group 2. And we had a pre-test, post-test design. I'm going to tell you a little bit more about the instruments later on. So at the beginning, we had a written test on fraction knowledge, a computer test, and then we had a phase of training, 2 to 3 weeks, where the experimental group worked with that tool that I just told you about. The second group worked with a more commercial, online tool that was helping them train more generally about fractions. So not fraction magnitude, more on processes, adding fractions and things like that. And the third group, the second control group, that had no training at all. And then afterwards, we would again do the computer test and the written test, and later on a follow-up written test. The special part about this design is that we also wanted to look at brain activation in these students. So in each of the 3 groups, we had roughly 20 students who also went into the fMRI scanner, and we had them do these fraction processing tasks in the scanner, and we measured, well, not us, our cooperational partners, measured brain activation. And that's actually where this logo that you could always see on the slides on the top right here came from. So we had a certain idea that a certain brain region would be active, or they know that a certain region is active when we process magnitude information for natural numbers, but it's not so clear for fractions. And especially, we were hoping that we would see an effect of the training, and that before there would be a more general activation, and later on a specific region would be active when kids process this information. Unluckily, we were inconvenienced by the corona pandemic, and during our intervention, the schools locked down, and we told the students to do the training at home, and also the post-test phase. We asked them to do that at home, but it's not so clear if the data that we got is what we can actually, how good the data is going to be. And right now we're at the follow-up phase, so the students are back at school, so at least we can have them do the written test one more time. Okay. Yes, for the instruments, so we had a computer test. So the question was, how can we measure fraction magnitude? And in the literature, there are 2 main tasks for that. So one is the fraction comparison task that Andreas already talked about quite a bit, and the number line estimation. I spent a lot of time choosing these 48 items for the fraction comparison tasks, because it's very tricky. There are many things that you have to take into account, as Andreas mentioned. So for sure, half of them had to be congruent and half had to be incongruent items, but also I had to take a look at distances of the fractions. For example, benchmark is an important issue, whether 1/2 is in between the fractions or not, just to make sure that we can identify certain patterns later on, and to avoid, what's the word? Confounding, yeah. Exactly. And the number line estimation task, that was a fraction symbol that was represented, and then a number line, and students were asked with the mouse to click the position that they thought where this fraction was. Yep. See? So, and then one question was whether this is a reliable way to measure fraction magnitude, and what the dependencies, what the correlations are between the different measures, and also between more general knowledge of fractions. So we had a written test where we could measure procedural and conceptual knowledge of fractions. Right, for the discussion part 2. So what we find is a great variance in these measures, and we think that they can be explained by different levels of understanding of the students, or maybe different stages of a learning process in these 6th graders. who are fraction beginners, right? So they just start formal introduction into fraction in 6th grade in Germany. And we're hoping that analysis of our data is going to provide more insight into this. And on the other hand, that we say that continuous representations seem to be beneficial for assessing and supporting students' fraction magnitude, but here also more research is needed. So maybe are there any questions directly to this part? Otherwise, Andreas would open up the more general discussion phase. So you can ask questions later on as well. So I would just hand back to Andreas.
Thanks, Johannes. Yeah, so just to add to that study, what we wanted to show here is, so we are trying to better understand how the fraction magnitude processing is related, first of all, to these bias patterns, if you do it in an intervention, so the causal effect, and secondly, to these more general measures of conceptual understanding, because there is a lot of discussion whether fraction magnitude is actually part of conceptual understanding, and how it is related to procedures. Like if you add fractions, for example, you can, if you use fraction magnitude, you can easily evaluate your result. If you have a half and a half, and you add the numerators and denominators, you get 2/4. If you have fraction magnitude, we'll see immediately, okay, that's not possible because 2/4 is approximately or exactly a half, so it cannot be this. So these are the interesting questions here. So more generally, as I said earlier, I think the large variability in the natural number bias patterns are defined in these studies that I showed, but also in other studies. So I cited one study that was published very recently with American university students with high math abilities who also did not show that bias pattern. They showed the reverse pattern actually. So they were systematically better. No, they were better and faster on the incongruent compared to the congruent items. We believe that this is also a sort of so the pattern occurs also because people use a lot of different strategies to compare fractions. So we ran a study where we asked these students immediately after each single item to explain how they solve these problems. And we got a whole list of strategies that many of them are mathematically not valid strategies to compare fractions, but they work on many specific problems. And so that's, I think, a very interesting issue to discuss also, that these are often heuristics that people use. And maybe, so I would question whether, bias is a good term to describe that pattern, because maybe it's more an effect of strategy use and or knowledge or understanding. And what I find interesting is that conceptual understanding is needed to know in which situations simply heuristics such as component comparison instead of fraction magnitude comparison, such heuristics are appropriate. So the mathematicians were obviously very, very much able to choose efficient strategies, but school students are not. And so this relation is not very clear yet, and it's not clear how we can teach to this flexibility that students are able to use flexible strategies here. So with on a very more general note, I would make the statement that I believe that math educational and cognitive perspectives are really necessary for a better understanding of learning processes and for advancing effective teaching. I think it's still important to say that because in education, I think we often do not teach things to students, but we do not always really understand what's going on in students' minds. And I think understanding that better is really important, but it's also, of course, related to cognitive psychology research. So thank you very much, and I would at this point also like to thank the many collaborators that collaborated in these studies and some of the agencies that supported this research. Thank you. People still awake?
Too many fractions.
So I would have a question.
Yes,
Okay. So A comment on the componential addition, as you called it, a frequent mistake. So it's like you have 1/2 plus 1/3, and you calculate it's 2/5. So that's also called the freshman's error. The interesting feature is that this is not an error in a certain situation, and that's I'm linking this to earlier talks on natural frequencies. If you have a natural frequency tree, the so-called freshman error or component addition is absolutely rational. So try to think about, take the typical, the most well-known one, mammography screening or cancer screening. There are 1,000 people, 10 of them have cancer, 9 test positive. So 9 out of 10 are positive. On the other side, you have, 990 who don't have cancer, but some 95 also. So you have 95 out of 990. Now you have 9 out of 10 and 95 out of 990. You can just add them up here. So the 9 plus the 95 is 104 out of 1,000. So it's not, that's the interesting thing. And natural frequencies are a situation where, which is to our best knowledge, the prototypical way in which humans and other animals learned information before the invention of fractions and probabilities and all of that. So here we have another, I think this just amplifies your observation that sometimes rules that are called biases are not all approximately right, yeah, but often they're exactly right, as in this case. Yeah? If you think a little bit broader about the natural environment of people.
Yeah, well, yeah, I think that's an important and interesting issue, and I think the question is like what to do about that or how to handle that in education, because actually one challenge is that a fraction is sometimes explained as a ratio or as a like 3:4 ratio, which is problematic if you think about this in the same way as you think about a fraction, because as you said, then componential addition is perfectly correct in that situation. So yeah, I mean, it's so. I think
so one thing to do about it would be some kind of revolutionary change the representation of numbers. So at least start with teaching with real numbers, as with natural numbers, and natural frequencies are a version of that. And when children master, like Bayesian thinking with that, then move on to probabilities and to ratios.
Yeah, I haven't thought about teaching the probabilities and natural frequencies, I should say, but there are some suggestions to teach fractions much earlier, so that students do not form these strong concepts about whole numbers first before they start with fractions. And one idea is also to use representations that students can use very early, which are, for example, continuous representations, because so this is basically proportional reasoning. And that's what students can do very, very early. There are lots of studies where students can solve problems in kindergarten age already. And I think one of the ideas would be to draw on that knowledge when teaching fractions. But it's it's still a challenge to do that.
If that interests you, I have at the Zoom version of this conference, there is a chat function. I put a paper on that, which is in print, the proofs, where I argue the opposite. So I argue, start with a representation that even second and fourth graders can understand. That's icons, no numbers, not Arabic numbers, nothing. And you can do base by just counting. And then move to Arabic numbers, that is natural frequencies, move there. And then people can do it the moment they have an understanding of numbers, and only then go into probabilities. I see your point, but I would argue that If you go the other way around, you will instill in most people the idea of a mathematics shock. I'm stupid, I can't do it. And I would argue go the other way, provide them some security. And often when I read some of these problems, I go back from probabilities to natural frequencies because I know that I'm safe, I can do it in my head. And that's also an aspect. We have burned too many minds, and they believe that they're too dumb to mathematics. And in truth, we are too dumb. We give them the wrong representations.
I guess it would be a great idea to run a longitudinal study and compare different teaching approaches, because this would be, I think, the sort of evidence that we would need to see.
Yeah. I invite you to look at this paper. It's called Do Children Have Bayesian Intuitions? And you find this from 2-year-olds to, from second graders to, I think, 7th, 8th graders, including we've studied children diagnosed with dyscalculia, and they shouldn't be able to do it. And they can't do Bayes with Eichener. They can't do it with natural frequencies. And the problem seems to be they can't translate Arabic numbers into a numeracy concept.
Yeah, thank you. So there is one question here, and there is actually a question in the chat.
In the chat, you can read.
I just read the question in the chat, which is, was the response time different for correct versus incorrect responses? Okay, I guess the question is whether there was a sort of bias effect within the accuracy, right? And so the answer is no. Accuracies were extremely high. These are actually seeding effects. And we did not see a difference here between congruent and incongruent items within the mathematicians' sample, if that answers the question. And then I think there were...
No, first Ulrich.
So, I have a commentary that is very much in line with what Gerd just said. And I wanted to use this opportunity to link what we've heard in this talk to what we've heard in the morning. So in this talk we've heard quite often the terms natural numbers and fraction. And earlier, before the lunch break, we heard natural frequencies. And natural frequencies, I think we also heard natural sampling. So how do natural sampling, natural frequencies, natural numbers and fractions relate to each other? This is what I now want to explain, and I think it's very important to be clear here. Yeah, maybe some little joke aside, but background. I think Ludwig's book is a hotspot. Hotspot means there are some people who understand what natural frequencies are. Other hotspots are Berlin, Regensburg, Lausanne, because there are some spreaders. And if we include the students, then we, I think, have more than 50 out of 100,000 inhabitants who understood the concepts. So, and therefore Ludwig's book is a hotspot, and I learned that you just came here, and the purpose is now to infect you. This is also in line with what you said. We need to integrate these people and get them affected, right? So, I give you now an example of natural sampling where we have no natural frequencies, and I give you another example of natural frequencies where we have no natural sampling. And I think from there I move on to natural numbers and fractions. So an example for natural sampling without natural frequencies. Imagine I, as a researcher here, ask my assistants to go in the street and have a random sample of pedestrians. They may use the timer method, so in random times there's a beep, and I take the first person who crosses this line and say, would you please come to me, there's this room, if you enter this room you get $100, just euros. Wait there for 5 minutes, then someone will come and blah. Would you be willing? Yes. So what I then have is a natural sampling. Do I have natural frequencies? No, because I haven't measured anything. So if I, as a researcher, come and say, dear assistants, did you do the job? The assistant will say yes. Here are the 22 people, and what are the results? Sorry, I didn't know what you want, what you're interested in. No? So we have natural sampling, but no natural frequencies. So I enter the room and I do this. Are you male, female? Are you above 18, below 18? and I count, then I also have natural frequencies in this natural sample. But there were some minutes where I had natural sampling without natural frequencies. Now the opposite was Hans Jörg, who talked about the Titanic with all these 1,000 passengers. There we had natural frequencies, but there was no natural sampling. That was the entire population. So, and these numbers that we have there, either in the natural sampling or in the entire population, these were numbers where we could say this is something that makes sense in relation to this 22 pedestrians or 1,000 something on the Titanic. And these are natural frequencies because they relate to some reference class. So if I have in my sample in this room here in Ludwigsburg, 22 people, 10 out of the 22 are male. Is 10 out of 22 a frequency, a natural frequency? Yes. Is it a natural number? 10? Yes. 22 is a natural number. 10 divided by 22 is a fraction. Out of these 10, 8 are adult. Is this 8 a natural number? Yes. Is it a natural frequency? Yes. 8 out of 10, is it a natural frequency? Yes. If I now say, out of every 100 people in this room, so out of each 100 people, 80 are are adults. No, out of each 100 males, 80 are adults. Is this a fraction? Yes. Is it a natural frequency? No. So this each does not mean it's a natural frequency. Natural frequency for this sample. And now the difference between this fraction. So 1 out of 5 can be a natural frequency, does not need to be a natural frequency. So if my sample is, let's say, such that I have 2 out of 10 have this feature, if I now say 1 divided by 5, it's a fraction, but it's not a natural frequency. Because I take it away and I kind of normalize or so. No? So, and now I'm going back to what Gerd says. I think it makes very much sense to start from natural frequencies, be they because I have a population, be they because I have a sample. But I have natural frequencies and I look at the relation between this. So these are all natural numbers, the relations are fractions, but if I start with fractions and then I hope to introduce at some point what natural frequencies are, people don't get it. Stefan, now this is something related to what we had in the discussion after lunch. So I often had examples where journalists report about our work and then they say, yeah, these researchers from Max Planck Institute, and they gave us an example for natural frequency, e.g. 1 out of 5. I say this is not useful and you may not even understand, you have no clue what a natural frequency are if you read 1 out of 5. It can be a natural frequency, but it doesn't mean that you understood the concept if you read 1 out of 5. So it's a natural number, it's a fraction, but it's not enough to explain what a natural frequency are, what a natural frequency is. And I think this is also what now Gerd said earlier. If you start with natural frequencies, the natural numbers and the fractions fall out. But if you start the other way around, first you explain what fractions are, and then at some point you hope you're able to explain how Bayesian inferences work. It's harder. I would start with the natural frequency tree and fractions come out of this. Not start with fractions and hope you can explain what natural frequencies are.
I didn't say that.
Or?
Jörg?
Can I just a quick comment on that? I think that's a nice, interesting way to think about. Just 2 comments, very brief. One is, in our talk we did not talk about natural frequencies at all.
I know.
And
you talked about natural numbers,
yes, I know.
There are these people who think natural numbers are natural frequencies.
And secondly, fractions in the way as we use the term. So here we are more talking about fraction numbers. So in German there is actually a differentiation between Bruch and Bruchzahl, fraction number. In English it's always fractions. But fractions can have a lot of different meanings and interpretations in the real world. So just leave it at that.
So actually, So my point fits exactly into, or speaks to that.
Speak the microphone.
So essentially, I think I'm speaking to two of your discussion points, and what I find, well, it's basically I would implore you not to use the word bias here. So because what you actually mean is people sometimes make an error. Given a certain task, then they make under certain conditions they make an error. And the reason why I don't think a bias is a good term here, is because there are numerous biases, or presumable biases in the literature that all relate to the perception of fraction information. And they typically have one of two patterns. So in some tasks, what you're really asking people about is they have to compare two proportions with each other. And that's the task you are also looking at. Which of the two proportions is larger? And then people sometimes make the mistake that for instance, they look at the numerator and they say, oh, it's bigger here than there, and that must be the bigger number. And that's called ratio bias in the psychological literature. It's also known as a phenomenon called denominator neglect. And it's also known in the marketing literature as unit bias. So we already have three biases here. The nice thing is they all mean the same thing. Unfortunately, there's also literatures that report the opposite phenomenon. And that's basically when you're looking at, if you're giving people fractions, and you're asking, for instance, what should people do? You can either save 10 out of 20 people, or you can save 20 out of 100 people. And then it's clear what you really should look at is only the numerator. And you shouldn't care about, so if saving 20 people is better than 10, regardless of the rate of the proportion. And people there often use the proportion to answer. So they basically, and that's called proportion dominance, which is also a bias, but it's the opposite phenomenon of the first. So, and that is also known as, I think it's called psychophysical numbing as well. So essentially what we have here is in the literature, as far as I see, there's 5 different biases, that fall into two groups. And I think it's basically total confusion. Nobody wants to speak to the bias of someone else, but everybody invents their own bias all the time. And that might be a good publication strategy, but it's not very good for theoretical understanding of a domain. So basically, I would suggest simply don't call it bias. Simply go with what you said at the end. So basically, there might be different strategies to solve this problem, or actually in terms of my perspectives, basically some problems ask for a different perspective. Some problems ask you to compare proportions, and other problems ask you to compare numerators, for instance. And then that's simply, they're different tasks. So it's basically, you're asking for, you can use fractions, or what looks like the same thing, the same construct, for different purposes. And depending on which purpose you're asking for, there's different strategies which are correct. That's my suggestion.
Yeah, thank you. No, just said thank you, because I think there's no need to comment on that, because it's basically, I got the same idea like after doing this work. I mean, we're just writing a paper where we discuss the use of the term bias, and this is, yeah, good idea. I mean, there is several other ideas why you could be critical about the term, and but I think we can discuss that later as well. So, but thanks.
Yes, I have just a comment. And furthering the two questions or comments before me. So maybe it is very good in schools to not just learn the right things in the right time, as Gert said, start maybe with those icon arrays, but also to kind of make certain changes in the language we use to talk about fractions and proportions. So I was thinking of, you could say 1 from 10 or 1 out of 10. And if you, as a teacher, make sure that you have your language there in order, it makes sense to speak of 1 from 10, because it's the 1 from those 10 instead of 1 out of 10. So this is just one example, but more generally, if you start to, let's say, as Gerd said, change the education and the order of the things you teach, you might also want to change a little bit the kind of language we use to express what we mean.
Yeah, thanks. I think that's a great comment. I just wanted to add here that I think in Japanese, I think people would say 10, take 1, or something like that, to a tenth. Yeah, I think maybe it's not Japanese or a different one.
1 take 10.
There is a language where people would say something like 10, take 1, and that could help
Chinese.
students understand what. Excuse me?
It is Chinese.
It's Chinese. Okay. Yeah. So I think more language issues that make things difficult, particularly with fractions and ratios and these things. So yeah, thank you. So I think we are actually also over
on
time or
okay.
on
We
time.
have plenty of time still in the discussion that.
Yeah. So thank you again.
Thank you. I also have a lot of ideas and discussion topics on this, because we know 1 out of 4 is not the same as 1/4, etc., etc. is not. So there is a lot to say, and also there is something to say about how to motivate that it is important to say whether 17/38 is more or less than 44/57. Why is that useful? And we know why, because if someone tells you in one country 33 out of 47 have this quality, and in another country it is 17 from whatever, we need to compare these. So there is a purpose, because it sounds a little bit absurd that you look at this task. What, why, what for? Yeah? Okay, so there are plenty of questions about this, but all of this is really related both to natural frequencies and to reasoning, Bayesian reasoning. So the talks are actually of today are all connected in some sense, the continuous representation, etc. And I think when we have the discussion at last, where everybody talks, we can treat again the questions that relate to your talk, which was very, very interesting. So now again, we make a very short break, and then we have the discussion. And please stay tuned. Have a short break, stay tuned, because we continue. And then I want to announce that there are some special issues coming, innovations in the artistic part. The artistic part was called the jam session on music. That will happen. But we also have some real art, some paintings, and there are some paintings outside in the Literaturcafé, that direction. And there will be a mini presentation by Jan Herrit showing a little thing that will last 5 minutes. And besides, we also have an aesthetic discussion and conceptual discussion on the possible covers of a book that was presented yesterday. So Constantino sent us 6 candidate covers. He received them yesterday. So because yesterday he presented the book, he asked us whether we can participate and help him choose the adequate cover 1 out of 6 natural frequencies. Have you understand? 1 out of 6. Okay, so we'll do that and now have a very short break. Thank you.